Welcome everyone to this week's Cassandra community webinar. We are delighted to have with us today Matt Overstreet, who is an architect at Open Source Connections. Open Source Connections specializes in solar and related technologies, and Matt is going to give us an introduction to the Cassandra Query Language. Before I hand over to Matt, I would like to talk about how we handle the question and answers. So if this is your first webinar with us, if you have a question for Matt, please type it in the Q&A panel in WebEx, and at the end of today's webinar, we will get through as many questions as we can. So Matt, welcome, and please take it away.
Hi, everybody. So we're going to get to some CQL, but we're also going to cover maybe some Cassandra for people that are a little more acquainted with relational databases and how that starts to map to CQL, so you have a good understanding of where CQL is coming from. And before I start, I want to thank John Berryman, who's been fairly active from Open Source Connections as well, who did some of the initial work on this presentation. This actually came out of some client work that we did around CQL. So we are going to do a quick overview of Cassandra. We're going to dig into the architecture of Cassandra and sort of how it works at scale. We're going to talk about how data is modeled inside Cassandra. We're going to do a little bit of strengths and weaknesses, which are pretty important to understand as you get into CQL, and then we're going to have a little bit of a practical example using some CQL. Douglas Laney from Gartner in 2012 has this nice long quote about big data. Big data is high volume, high velocity, and or high variety information assets that require new forms of processing to enable enhanced decision-making, insight discovery, and process optimization, which I think is true. I would sort of narrow it down to you're in big data, maybe if your data is coming too fast for you to record in a traditional way. You can't write your database indices, or you just can't get it all written in one hard disk because it's coming too quickly. The data could be so large that it just can't store on a single node in your network, and now you're coordinating between nodes, and that has a whole bunch of very, very difficult problems. Or it could just be that the data's too dirty to store in a strict schema that we all came up with in doing relational database work, which sort of leads to the new V on top of the new C on top of the three Vs, which is complexity. Why is big data so tough? Maybe I'm going a little deep here just to come back up and talk about CQL, but I think if you have a sense for a couple of these things, it's going to make it a lot easier to understand why CQL does what it does. The main thing we find ourselves talking about is this paper by Brewer that's referred to as the CAP theorem or the iron triangle. But Brewer had said there's three desirable things for a network system that does anything. We talk about it with databases all the time, and that's often where we talk about the CAP theorem, but it's a little broader. The three things that you might want that system to do is you might want it to be consistent. No matter where you talk to that system, no matter what node you talk to in that big, broad system, you want it to give you the right answer at that moment in time. You don't want two nodes to possibly be able to give you two different answers. You want it to be available. If you send a request to it, it should respond. And you want it to be partition tolerant. Network links die, machines go down. I always talk about it as the time traveler dilemma, where a node goes off the network, comes back on network years later, just a couple days later, and then all of a sudden you're dealing with the problem of reconciling what it thinks is true from 2 days ago with what the network thinks is true now. And that seems like it ought to be an easy idea, but clocks and big networks maybe aren't as easy as you would think on the outset. So what Brewer said is you can't have all three. You've got to pick two. And for those of us that did a bunch of MySQL, the two that we picked were we wanted the data to be consistent, and we wanted it to be available. So we have one node, and until that node dies, which is essentially a partition failure, that data is consistent and we'll get a response. HBase, we said we wanted to be consistent and we wanted to be partition tolerant, so it knows when it loses nodes. It's got the data replicated. It can do something reasonable about it. But if the controller goes down, it may just disappear and we won't get a response. And then with Cassandra, we've said, well, maybe the two big things for the problems we want to solve with Cassandra are that it should be available, it should always respond to us, and it should be aware when partitions happen. And there are some cases where maybe we want to trade between those in consistency. And so let's make this consistency tunable. And you'll see examples of that as we build up to CQL. So broadly, how do we do big data? We denormalize everything. We flatten it. We get rid of the joins as much as we can. And the reason we do that is we need the data to be able to shard anywhere that we want it to go. And we need the related data to be near each other, or we have to do a bunch of network coordination. And it sort of turns out, when we've got a lot of data on a lot of nodes, that sharding is a much more difficult problem than dealing with data normalization. And if you are a stickler for data normalization, you're going to have trouble at these scales. And it's just something that people coming from a more relational database are just going to have to make a decision about. They're just going to have to become accustomed to it. What that means, no joins, no transactions, essentially. There's a potential for inconsistency in the system, and there's no transactional guarantees. There are ways to work around that, but it is something to keep in mind. Querying is vastly simplified. This is such a weird point. You're not going to do this sort of domain-specific data modeling where you're trying to match the data model in your relational tables to the concept, the high business concepts that you have for what the data ought to be. You're going to be modeling your data based on how people are going to access it, not what's in it. You will do what John liked to call query modeling, and I think it's a good thing to keep in mind. We're living in a world where performance is key, and the interaction with the data isn't some platonic idea of what the data ought to look like, but it's how people are actually requesting it. What do you get back from that? You get some crazy scaling ability. There's not a lot of deterioration as you add nodes. It's really impressive what the Cassandra folks have been able to do as far as scaling up. How does Cassandra fit? No single point of failure. We'll see a lot of that. It actually writes faster than it reads. A lot of you probably know that, but for those of you that don't, you're probably scratching your head now. And as we said, we can sort of tune between consistency and availability, depending on our concerns. So let's talk about the topology and behavior that allows us to do this. You'll hear a lot of people talk about Cassandra's ring architecture. It's a good way to think about it. There's no single point of failure in the ring. You might think that the ring itself would be a single point of failure, but it's really a logical idea. It turns out that having the nodes talk to each other in a gossip-based protocol allows them to sort of bend their way around network failures. And as we'll see, node failures can be dealt with without a loss of data, and gossip allows us to deal with weird network behavior without a loss of data. And probably most critically, it's democratic. There are no special nodes. All nodes do the same thing. They just are responsible for different slices of the data. And here's an example of that. We have 6 nodes here. We have this idea of virtual nodes. Our data is sliced up. You could pretend like this is the letter on the side of an encyclopedia, and we're looking for things by name. In truth, these are ranges of hashes of the row key, which will probably emerge as we talk about it a little bit more. But the key thing here is 6 nodes, whatever A represents, whatever range of data A represents, you can see we've got it on node 1, we've got it on node 2, we've got it on node 3, and that replication is true wherever we go here, which means we can lose node 1, and then we'd be fine. We can even lose node 2 and we'd be fine. And we're not, with this replication factor of 3, we're not in danger of losing data until that third node goes down. And hopefully by then we've gotten in and done something to protect ourselves from that. So we are very fault tolerant. I'm not going to dive into this slide, but I do want people to be aware that as of Cassandra 1.2, the data partitioning got a little more complicated. It's worth learning, but the main thing that this gives you is it's a lot easier to just add one node. But with the old data partitioning scheme, it was sort of, if you want to do it an easy way, you just need to double the size of your nodes, and now it's much easier to just sort of expand. So let's talk about rights. So a client from the outside would make a request against any particular participant inside the Cassandra cluster. So we hit node 10. Node 10 says, hey, I know where that row key that you're talking about is, and it's on node 1, 2, and 7 based on the information I have, and it sends a request out. Or it says it should actually be written to those, not it's on. I'm talking like it's a read. It should be written to nodes 1, 2, and 7. It sends a request to all of them to write it. And then it gets a response back. It tells the client, we're good, it's written. The thing to maybe keep in mind here is this is where our tunable consistency comes in. And this is where you will make some decisions about how consistent you really need things to be. These are the 3 nodes that have the answer. If I say I'm going to write and I only care that one of them tells me they're good before I tell the client we're good, that's consistency level of 1. If I say I want half plus 1, essentially 2 in this case, to tell me they're good before I tell the client we're good so that I feel better that the next read's going to get a good response, then I say I want a consistency level of quorum. And here 1 and 7 or 2 and 7 or 1 and 2 would need to respond. And then if I'm very paranoid and I want to know that every write commits to every node that might be queried, I can tell Cassandra that I want the consistency level to be all, and that's slow. So often when we're dealing with these solutions, we're dealing with it because we have such high throughput that we can't afford that slowness, but that's something to consider as you're putting this together. Maybe a little off the base with CQL, but I like to talk about it anyway. Reads, similar idea. And if we think about our consistency level here, consistency level of 1, we're fine. Node 7 came back. Consistency level of quorum, we're fine. We got essentially half rounded down plus 1. Node 1 could come back. Consistency level of all, we're going to pretend that node 2 here is actually down. What's the result of that? We have an availability problem because we said all nodes have to respond that have a copy of the replica that we want for that range of key values. Node 2 can't come back. We really can't give the client an answer. Another thing here, if you're not familiar with it, with a consistency level of quorum, it's possible, or 1, it's possible that maybe these nodes have different answers because somebody went to sleep or hopped in a time machine. If we see that on a read, we'll actually kick off a read repair to take care of that. So there's some other guarantees to sort of fix consistency problems that maybe fell through the cracks here. All right, so let's talk about how we want to model data and how we sort of map your domain to Cassandra for whatever problem that you have. Again, I know this is pretty fundamental, and people that have been working in Cassandra know this. I just think it's critically important to talk about this a little bit before we talk about CQL, and if you really do grok this, then your CQL experience is going to be a lot more pleasant. So in Cassandra, we have a key space. It's roughly analogous to a database in a relational database. Inside the key space, we have column families. I feel like our analogy sort of breaks down here. I want to call these tables, and in a way they kind of are, but some of the things we think of being defined in tables really come from lower elements here. In each column family, we have a lot of rows. and in each row, we have a lot of columns. I really should update this image because what I'm showing you here feels a lot like a very heavily structured relational database schema, row or column, 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 column. But if you can imagine that this is my time clock and I have only been working here for a little while and I have checked in 3 times, I might only have 3 columns, 1 for each check-in. Whereas somebody who's been working at the auto manufacturing plant that I'm using as an example here, who's been here for 12 years, might have a lot of columns in their row. And that's, you'll see more in our example later, but it's really important to understand that these are not some sort of strict schemaed columns. These are data entries in a row that we refer to as columns. That word is a big catch for people that are trying to come over from a more traditional relational database. Inside a row, we have essentially 2 different types of elements. We have a row key, and then we have the individual columns inside the row. Row keys are how we actually locate the row across the entire cluster. They're the main way that we'll track data down. The more you understand that, again, the more efficient your queries are going to be. That's a big deal. Row keys are how you get to the meat of the data you want to interact with. And if you can't include a row key in your queries are going to get slow, and they're going to get indeterminately slow. So it's just something to bear in mind. It's really the difference between happiness and unhappiness with queries for me is watching people figure out the role of that row key. You need to think in terms of that when you're designing around your queries, which is how you're structuring your data now. So inside a row, we have columns that feel a little bit more like key value pairs that can just go on until the end of time. A column has a column name, has a value, or a tombstone that lets us know it's been deleted. Those have to stay around for a while because remember we have multiple replicas and they might have to reconcile. So having a column that has no value or having a column that just disappears, we don't know at that point if that node never got the new column or it got a delete and it didn't get to the other nodes. It's very hard to work that out. So tombstones are left to deal with that. There's a timestamp and a time to live. Time to lives are pretty cool. I haven't really done enough with them, but if you look around, you'll find some fun stories about them. I imagine if you were doing things like roll-up tables or writing like sequential data that came off a live stream somewhere that you only wanted to have available for your cool dynamic dashboard for a short period of time, you could use the time to live. And in fact, later we'll talk about how deletes are sort of an anti-pattern. So if you know how long you want something, don't go in and delete it later, but give it a time to live instead. So we could have a ton of these, column, 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 column. There is a limit. We'll talk about it later, but it's a big limit. See if I hit everything there. Timestamp, yep. Row key, column name, column value, they all have data types, and those data types are the things that you're used to, string, int, long, whatever. If you've been dealing with programming or databases for a while, you have probably a pretty good sense for what's available for you there. This is a little cryptic, very important. Column names have a comparator. The main thing to keep in mind with that now is to think about the fact that column names are essentially sorted. You'll see a little later where it feels tricky, but I make a column name a date for a tweet stream that's coming in. What that means is if I inject a bunch of columns into this row and they all have a date and a time and a second, I start to get back my ability to do maybe some limited range queries within a row or greater than within a row, because it's very easy to say, all right, well, I want everything bigger than noon yesterday within this specific, assigning a specific row key. It's very easy to go cut that off and return back the remainder. We do that so often in relational databases, and it's a stumbling point, I think, coming into CQL. Understand that column names are sortable and that you can get a lot of really good things done with that, but you will have to think about that as you're building your schemas, how the column names are built and how that affects sorting. Row key has partitioner. All that I really mean by that is the row key is how you know what node out in the cluster, what virtual node it goes in and what real node it goes in, and that's, you don't want to start searching across partitions. You want to be able to come down to that row key. Rows can have any number of columns. We talked about that. Rows can have lots and lots of columns. I'll show you an example of column values being omitted. I'm not sure how useful this is, but it's a little hack, and it might help you understand what's going on here. Oh, okay, I haven't gotten to it yet. I'm going to do a really quick step through on writes and reads, and then we're going to get into the more of the schema design and CQL stuff. I said writes are faster than reads. I'm going to show you why, and most of it has to do with not touching the disk any more than we need to. Write comes into a node. First, the coordinator way out here gets the write request. Make sure, based on the row key it'll have, that it sends it to the right nodes to write it. They'll write it to their memory table and not even touch disk, which would be great if we didn't worry about persistence. To give us some persistence, we're going to write it to a commit log. That's a really fast sort of streaming operation. And that's it. We're done with a write. We'll clean it up later and get it into our SS tables, but it's ready to be queried. It's committed to disk. It's stable. And structuring it this way means that we actually will block on CPU before we block on disk I/O, which is amazing. Let's talk about reads. I said writes are faster than reads, and I'm going to show you why. Read request comes in. Maybe it's in the memory table. Maybe we get a super fast read. If it was written recently, reads are going to be super fast, almost as fast as writes. If it wasn't in the memory table, we do have a cache out here for rows that have been retrieved recently, and we'll go to that row cache, which is really fast. That's sitting in memory. After that point, anything we're going to do really needs to touch the long-term storage, the hard disk. We want to avoid that because that's going to add orders of magnitude to the amount of time it takes for our node to respond. So we have this little Bloom filter, and Bloom filters are kind of interesting. The Bloom filter can tell us if a row key is definitely not stored on this node. We know it should be here if it exists. The row key will tell us not that it is here, but it will tell us that it is definitely not here. If you think about that for a second, that's really useful, because if this says no, we can go back to the client and we never touch the disk. If the Bloom filter says maybe, then we've got to go hit the key caches on disk. We've got to go hit the SS tables and get a response. And here's our slow read, because we've gone to a big involved disk process to track it down. So let's do a practical example of all the stuff that we've talked about that we can then tie back up to CQL and wrap this whole thing together. So here is an idea of something we might do, a Twitter stream reader that we might build. We have 4 column families, followers of following relationships, tweets and timeline here. If you're familiar with Twitter, this might be a little confusing, but tweets are the things that a user said, and timeline are the things that a user might want to view from all the people they're following. So you can really think of these statements really as pseudocode. Some people might be more familiar with what this is, but as we're talking about CQL, it's still useful before we get into CQL to just sort of say, here's a notional pseudocode around what we want to do. So let's say that Nate follows Patricia and we want to map that. So we set in the followers column family, the row key Patricia, we're going to put a column in it called Nate. And in this case, we're going to pass an empty value. This is an example of the column name being enough data. If it exists and it's got an empty string, we know that that's a follower. John and I debated this a whole lot, and I said, if it were me, I would write the date that Nate followed Patricia here instead of just an empty string. But it's worth noting that they're kind of 2 places to stash data in a column. the column name, because it can be anything you want, it may just be enough that the column exists, even though there's no specific value in it or, you know, some sort of low information density value. All right, we don't have joins, though, and we really don't have reciprocal relationships. So the next thing I need to do is set in the column family following. The row key Nate needs a column named Patricia. And again, we're just going to pass in the empty value because we can't do, because we're pretty heavily denormalized, we can't do a join here. We can't look at that relationship back and forth. We don't have any, I guess we wouldn't really do that with a join. But so an example of storing data in column names without values, it's denormalized and it's redundant. And we are trading off normalization for the ability to shard, like I said earlier, and for the speed that we get. And we're, I think, probably all running into problems where that's a choice we have to make. And Cassandra does a good job with it. So say we wanted to get all of Nate's followers, we could get from the column family followers for the row key Patricia, and we'd get all these people back. One thing about this example is it's actually wrong, because remember I said that column names are sorted, they're comparable and they're sorted. With these string column names, they should actually come back in alphabetical order. Not a big deal, but a nice way to reinforce that idea that these are always going to get sorted into a nice, pretty order, and it makes it easy to do some of the range operations that are a little cryptic when you hop in and start data modeling. So we make some tweets. Set, column family tweets, row key name. Here is our column name. See, it's a date here, and the value is wonderful morning, this coffee's great. We do that again. Set, column family tweets, row key Nate, column name is a date. That's just fine and great, because remember, these column names are getting sorted, so that makes it pretty easy for us to do ranges within this very narrow scope. And here's another tweet, and here's another one. And we could get the tweets for Nate, and you would get them all back. And remember, you would get them all back in the order, in the comparable order of the column name. CQL is a convention. It looks so much like SQL. We're going to apply that to what we've learned so far, and then we're going to map the two together. And that's the big thing that I want to impart, and I hope that's very helpful to people listening. This create table should look very familiar to anybody who knows SQL. ID, time, UUID, primary key, last name, first name, date of birth, with the data types. If you are the type of person that runs ahead, you probably already scratching your head over what this looks like inside everything that we've talked about up to this point, and we'll get to that. With CQL, we can do a lot of the things that we expect. Insert into users, ID, last name, first name, date of birth, values. Now, this now is not bringing us the data, it's actually bringing a universal unique ID for the time and putting it in for the ID. Not something I'd recommend for the ID, but anyway. Last name, Berryman, first name, John, date of birth. That's John's date of birth. All you need is his home address and social security number, and you can become him now. Here's an update query. Update users, set first name equals John, where ID. So we've just done the same row. We've done an update query just like you'd be used to. This all should feel very, very familiar for people that have done SQL. Select date of birth, first name, last name from users. And this looks like a table, right? This doesn't look at all like the data we've been modeling in Cassandra at this point. So how does this map to Cassandra, and how does that impact the searches that you're going to do with CQL? Here's a create table statement. We're going to create an employees table, company text, name text, age, integer, role text, primary key, and we've got this weird compound primary key. This is very important. Look at what happens with this as we talk about this. So here's sort of the notional thing that we'd expect from a relational database. Company, company, name, name, age, role, primary key, right? what does this look like in Cassandra? We have 2 rows. Each row has a row key based on the first part of the primary key, OSC, and in this case, another company, RKG. The second part of the primary key is used inside the column names to drive the comparator for the column names. So what we see now is for OSC, for Eric, his age attribute is 38. For OSC, for Eric, his role attribute is dev. That's funny. He's supposed to be CEO, but that's an inside joke. That really should be CEO there. Don't get too confused by that. For OSC, for John, primary key company name, for John, his age attribute is 37. For OSC, for John, his role attribute is dev. And I could walk through these again. What does this let us do? It's a lot easier to query. As long as our select query says, I want the company to be OSC, we can now have performant queries that say, I want the company to be OSC, and I want the name to be Eric. If we did that query for name equals Eric, and we didn't tell them what company, we have to hit every row in that key space and essentially interact with everyone. And so we're dealing with however many rows there are, and that's the main thing that I want people to take away, because that's the place where you're going to get caught. It's the place where I've gotten caught in CQL is maybe I omit this, and then I feel like I should be able to search by name. But if you're not scoping, if you don't understand what it gets turned into in these rows, you're going to get queries that just literally can take just an indeterminate amount of time. So what's our modeling strategy, knowing all of that? John likes to say, don't think about the data structure, and I like to say, don't think about the academic data structure. You need to think about the queries that are going to come into the system, and you need to model for that. You've already made a decision that it's too big or too slow or too whatever for a traditional relational database, and the way you're going to succeed and get that speed is you're going to have to start, building your Formula One car that maybe doesn't run to the grocery store well, but can run a lap really, really quickly. And you need to understand what the differences are that make it able to win races and do what you need it to do, but you are specializing. Consider what's efficient in Cassandra. Writing. We see nodes write 4,000 writes per second per core on the nodes. It's great. That's so fast. Retrieving a row is efficient. Retrieving a slice inside a row, where we talked about column names in order, retrieving a slice of column names is great, fast. Those rows a single row will only be on one node. A slice is super fast to get back. We know where to get it. We know how to cut it. Retrieving in that natural order, which we can control. That's the comparable column names. Write the data in the way that you're going to query it. Remember that disk space is cheap. Denormalize. One thing that was talked about at the last Cassandra Summit that I loved was, if you think you can't write a query because you just can't get the schema to work to make that query performant, maybe you want another column family and you want to write the data twice in 2 different ways, and just make sure you've got some security to clean it up when the time comes. But disk space is cheap. Duplicate the data all you want if that's going to give you fast queries. And separate read-heavy and write-heavy tasks. So what are the anti-patterns? What do we not want to do that maybe we do in relational databases? A lot of times we'll read a value and then write a value. Don't do that. There's a sort of a soft consistency guarantee. Reads are very slow. Don't try to avoid finding yourself in a place where you're saying, oh, let's check this value, and then if it's this, do this, if it's that, do that. Doing any sort of heavy deletes scatters all this junk through the SS tables. Your Bloom filters actually become much less efficient. So you're going to disk for data that doesn't exist anymore. It won't be fixed until a big compaction that's often set to about 10 days. Use your timeouts if you know what time data is not going to be relevant. But if you're in a use case where lots of deletes need to happen, maybe you need to think a little bit more about it. A lot of people find themselves trying to turn Cassandra into a distributed queue, and you need much more severe consistency guarantees to do that, and it's just not the right application. Don't do joins. And the other thing to keep an eye on, I like, this is actually John's terminology, super wide row sneak attack. You do need to bear in mind that at some point, if you get above 2 billion columns in a row, things are going to go wrong. So as you're modeling, just remember there's a limit out there. And that's it. That's what I've got for you guys. So where I'm able to answer questions, I'm happy to.
Thank you very much, Matt. So a reminder, we do have some questions coming in the queue, but a reminder, if you have a question for Matt, please type it in the Q&A panel inside of WebEx, not the chat panel, and we will get through as many as we can. So, Matt, are you ready?
Yeah, I am, and I wanted to thank, I at least got one typo correction. I'm clearly an engineer, so thank you for the typo corrections as well.
Okay, great. So,
oh, go ahead.
The first question, Matt, to you is, and you touched on this a bit with talking about tunable consistency, but can you just talk about consistency level in general? Maybe spend some time explaining what we mean by eventual consistency would be great.
So oftentimes when we're writing something to a data store, the best guarantee that we can have is that I write, say 3 of us are in a room and I want everyone to know a fact. I'm going to the dentist tomorrow at 2. I want to make sure everybody at work knows that. The best thing I could do is just go to everybody, get them all together and tell them all at the same time that that's going on. And then I have a very consistent situation because no one's going to get confused about what's going on. They were all with me when I said it was going on. The much less consistent version of that, or the one that has a less consistent guarantee, is if I told somebody on Tuesday and asked them to tell everybody else, and then somebody might not find out until Wednesday afternoon and they've already scheduled a meeting for me. That's okay. Sometimes you only have time to talk to one person, and scheduling a meeting to make sure everybody's on page, we all know that that's not always worth your time, right? But I think that's a fair analogy for the idea of strict consistency versus eventual consistency. The other thing that I think about is Cassandra coming out of Facebook and supporting everybody writing their profile status. Well, it doesn't really matter that everybody has immediate access to the absolute current version of everybody else's profile status. We can wait 100 milliseconds. Alternatively, if we were all in some big system and we were pushing around monetary purchases, money elements, we want to freeze that system and make sure that there's a transaction, everybody's up to date, no loose money stuff is going on, and that puts a lot of constraints on a system to enforce that level of consistency, particularly at tens of nodes or hundreds of nodes or thousands of nodes. Does that answer the question, do you think? Is that what people were looking to find out?
Yeah, I think that is spot on. Thank you, Matt. So a couple of questions around TTL, time to live. So maybe we can group these together, one from Daniel, one from Raj. So first off, Daniel asked, can you be notified about a time to live expiration?
And I don't know the answer to that. I've only played with time to live fairly shallowly. But I bet we could pretty quickly do a Google on that and figure out the answer. I feel like every time that I've done it. Oh, go ahead.
what I was going to say is any questions that we cannot answer here, the IRC and the mailing list for Apache Cassandra are very, very active. And also Stack Overflow is a great place to ask Cassandra questions. Experts from DataStack monitor all those, and then also, tons of people from the community as well.
And I'm sure people smarter than I would disagree with this, but part of the reason I can't answer that is I view that as kind of an anti-pattern. If I have set a time to live, I know that past that time to live, Cassandra's not going to return that value to me. And so I don't want to build around being notified. I want to build around being comfortable that I've said, after next Tuesday, this data is not valid anymore. And I'm just going to assume that's true. So if you have a case that needs that, I think you're right. I think the forums could be really helpful.
Yeah, that's a great point, Matt. So the other TTL-related question here from Raj is, how can I do mass deletes? We are storing session data that doesn't have TTL set. I'm not sure if I can change the TTL. What options do I have?
I believe that you can do, and we'll double check on this. I believe that you should be able to update those values with a TTL. And then, the other thing, and I might farm this around to a couple other people, but the other thing is, if you're moving over to using time to live and that's your new architecture, it might be that you just want to find a time when the system's not really busy and look at doing some type of mass update or delete and then getting a compaction really soon afterwards, because that mass delete is going to slow down your cluster. Maybe you're worried about finding the rows, and I don't know that I have the answer to that, but if you're worried about the performance impact of your cluster, you definitely want to schedule a time for that and then get a compact in after you do that.
Okay, great. And I will answer this one. Wilfredo asks, can I get emailed the presentation? So there is a community website called Planet Cassandra. We post all the presentations and also the archive of the video. We will place there within about 24 hours. So, this time tomorrow, you can go to Planet Cassandra and the recording and the slide deck will be there. Jeffrey asks, how do you create a table where the row key is 2 values?
So the row key is whatever you tell it to be. So you could just smash the 2 of them together. The row key is almost the secret information you have. I think I saw another question about how does the row key get generated. And essentially, you do. You decide what it would be. If I had a bunch of Twitter people, maybe the row key is all of our names. If I had a bunch of Twitter people and I was worried that so much content was coming out that I wanted to split it by month, my row key might be Matt Overstreet, January 2014.
Sorry, say that last bit again.
Oh, I was saying if I had so many columns that were going to come in a row that was just, Matt Overstreet, I might say Matt Overstreet, January 1st, 2014, and that would be my row key. Maybe the Twitter example is a little interesting for that too, where each of our Twitter row keys was essentially the name of the person. But ultimately, you decide what the row keys are, so you need to come up with a convention, and it really does need to be something that you know so that when you're querying the data, you're not searching for the data, because if you're searching for the row key, you're going to get really slow performance because you're just going to have to talk to every node. If you think about how the coordinator works, you call the coordinator and say, here's data I want you to put, and here's the row key for it, or here's the data I want you to get, and here's the row key and maybe some other criteria after the row key. And if you don't provide that, you're probably just going to get a warning from Cassandra saying, I don't know if you want to do this because it's going to take forever. So it's not like an object ID in a database where it's generated for you. It tends to derive out of your data. we did a bunch of work with the Patent and Trademark Office, and so row keys were patent application numbers because everybody knew them. It was easy to search for them because they were usually available at the time we wanted to search, and they were unique.
Okay, thank you. Todd is asking, any limits on data size, strings and blobs?
Yeah, and I don't remember what it is because I'm sort of focused on the 2 billion rows. I feel like there's a limit, and I don't know it, but it's, yes. I guess I could technically answer your question, but I'd feel very shallow about it. Yes, I think there is. But you're going to have to look around a little bit to find out what it is. I haven't dealt with it in a while. Do you remember there's a limit on the number of columns in a row, though? What was it? And what we were doing was the last time we had to deal with it, and it was actually patent related, we were splitting them, and we were actually using the column names. So like a trivial example is if you had a patent and you wanted to save it in a row, you could make a column named page 1 or page colon 1, page colon 2, page colon 3 to make sure that you weren't putting too much TIFF information in an individual. But I feel like it's bigger than one page of TIFF. I just don't recall it right now.
And Adam is asking, can you explain in a bit more detail how Cassandra resolves a failed write to a node?
How Cassandra resolves a failed write to a node. What you're not going to see is a lot of failed writes to a node because there's no rules to prevent you from writing. It's going to get pushed into the mem table. And it's going to be written to the commit log, and Cassandra's going to say, I got it, and respond. Where you're going to see a failed write operation to the cluster is if you say we had a consistency level of all, and we had a replication factor of 3. So there are 3 nodes out there that hold the data, that could potentially hold the row key that we're writing. And if our consistency level is all, and we send a write to all 3 of them, and one of them doesn't respond, that's a failed write, and we're going to let you know that it's an availability problem. We just couldn't do it. With quorum, if 2 of them failed in that example, then it would be a failed write, and you would be informed that it was a failed write. And with a consistency level of 1, as long as that one node that was up and running was alive and came back and said, I wrote it, it would be a successful write.
Yeah, I think there are so many cases actually of people run Cassandra for extremely high availability. It's always on. Mm-hmm. If you're replicating to multiple data centers, you can actually have nodes go down and not know it for weeks and weeks and weeks and weeks because your writes get written everywhere else and your application keeps on going. So, very robust in that regard.
And I feel like that's one of the big things that if that's a concern for you, that's something that you really want to think about and maybe do some testing on, because there are, I've talked about the consistency level of 1. There's a consistency level below 1 that basically says if a coordinator says, yeah, I got it, and doesn't even really get it out to a node, it'll tell the client that it wrote fine. And say you're streaming lots of traffic data and you don't care if a little bit of it gets lost, but you want to make sure that as much of it as can be written is written, that might be fine for you. Whereas if you're recording medical records, you might say, no, you've got to write to every replica, and if you don't write to a replica, then the taser underneath my chair needs to be triggered remotely using some sort of neat remote network protocol, and let me know. And so a lot of the concerns there around consistency really have to do with the guarantees that you're making with the data. Because a lot of times with big data, it's about having the vast majority of the data, because we're going to make assumptions on the vast majority of the data. And if we can't put the infrastructure in to get all the data cleanly, that's okay. as long as we get 99.9999999% of the data, and that's enough for us to make a decision on.
Yeah. Tana asks, so I'll answer this one a little bit, and then you can weigh in, because actually this is one we get asked a lot, and it's a common misperception out there, and it's one of the reasons why I hate the term big data. So Tana asks, is it worth using Cassandra if I don't have big data? So the short answer is yes, absolutely. Think about what your application needs. So we talk to tons of users who have terabytes and petabytes of data, no question. We also talk to tons of users who have what would be termed very small data, a few gig. So, but what they have in common is usually the type of data and the speed at which the data is entering the system. So if you remember, Matt talked about, Cassandra is fantastic at writing data very, very quickly. So if you have, let's say, time series data streaming in from different systems and you want to get that written and preferably write that data to multiple locations, multiple data centers, Cassandra is an excellent choice for that, even though the size of your data may actually be very, very small. So Matt, I don't know if you want to, you probably hear this from customers quite a bit, I would imagine.
I do, and I've gotten a little tired of the big lofty definitions of big data. Big data to me is like saying the word heavy. My definition, my real definition of big data is data that's just too cumbersome for you to do what you want to with the tools that you have. I prototype a lot in relational databases when I don't really understand how the data is going to be used, and then I move to more performant things as soon as I realize, hey, data's streaming in really quickly, and maybe I don't have a lot. Maybe I have a meg of data, but it bolts in at high capacity from 27 different emitters out there in the world. I'm reading air conditioner data from a bunch of buildings in a facility, and it comes in fast, and there's never all that much of it, but concurrency guarantees, or consistency guarantees, sorry, I do that all the time, would make that really, really big thundering herd of data lock up and not work. That's a big data problem. It's the spot volume. So it's not necessarily about having petabytes. It's about saying when I need things to perform to solve the problem that I have, is this the right way to do it? The other question, the other answer to that, which is kind of a funny answer to that, is be careful about production installs, but a lot of times, by the time we get to big data, we haven't practiced with the tools we need to use them. So I think occasionally it's really nice to use a quote-unquote big data solution for a non-big data problem, just so you can get a feel for it. It won't be quite like using it in anger where that camera data is streaming in faster than you can deal with it, but it will get you ready when that happens, and maybe that's enough of a reason sometimes.
Yeah, absolutely. So Uma is asking a question about create custom index. Where is the custom index Java class documented?
Yeah, I don't know. Unfortunately, I don't know that at all.
Yeah, so tons of documentation on datastacks.com. So and good information about Java class there. So I would definitely hit that up. So can you explain what the Bloom filter is, Matt, and how it works?
Yeah, I can. This is a good challenge. So everybody's familiar with the idea of creating a hash from a piece of content. This is this idea. Maybe we have your resume, and we hash your resume down to 16 characters. And we use that hash sometimes. We used it a long time ago to see if a file was the file that we thought we got. So that's the key thing to understanding a Bloom filter. what a Bloom filter does is it says, for any piece of data that I get, I'm going to hash it a couple of different ways. And I've got a little checkboard. Say we took your street address and we could hash it down to one number, which is legitimate. It's not a very useful hash, but we could have a rule that takes any address and figures out a hash for it of a number between 0 and 1. And then we had another one that hashed it down to a letter, and another one that maybe hashed it down to 16 characters. Admittedly, there are thousands of addresses in the world, so if we just check to see my address resolves down to the hash of the number 1, well, thousands of other addresses would hash down to that too. So it wouldn't be a really great way to tell whether or not my address, whatever you're checking, matches my address. But if we use multiple hashes, that space gets smaller and smaller. So if in one algorithm my address hashes down to 1, and in another algorithm my address hashes down to B, and in another algorithm my address hashes down, just to be silly, to the color orange, I can build a table that says, on this disk, I have a document that hashes down to orange. On this disk, I have a document that hashes down to 1. And on this disk, I have a document that hashes down to B. Why is this useful? This is useful because I have the computational power when a new document comes in to hash it 4 different ways. And then I can look at this matrix of the result of all the other documents that have been put in, and I can go, all right, this hashed to 1C orange. You know what? No document within my index matches that. So I don't need to go to disk. And it's this idea of sort of abbreviating your document into a hash 2 or 3 different ways, putting those in memory and saying, it can tell you that a document might exist, but what it can really tell you is that row key does not exist. There is no reason for you to spin up a platter on the disk because I can guarantee you that it's not there. So it produces lots of false positives, but it never produces a false negative. And this is great when you're talking to a node in memory and that node is responding and saying, hold on, let me look for it for you. If that node can say definitively it is not on the disk, then it can come back in milliseconds. I guess it can do that either way, but it's an order of magnitude bigger if it has to go to disk. And it is a huge and very useful thing that's going on in Cassandra. I don't know that you need to understand it other than academically, but if what I said to you doesn't make sense, open up Wikipedia and search for Bloom filter. It's a really neat idea.
Okay, and Matt, there are so many more questions. We aren't going to get to them today, but we are implementing everyone something a little bit new. So every month we will do a monthly just Q&A webinar where we'll get through as many of these questions as we can with a panel. And then also we are going to be starting off, we have a couple of community evangelists at DataStax, Patrick McFadden and Al Toby. And they're going to be starting up office hours where if you have specific questions like this, you can just dial in at a certain time and ask your questions, you know, basically some free consulting. Matt, I know you're on Twitter, and are there other ways to contact you if people have questions for you or other experts at Open Connections?
Twitter is great. Open Source Connections has a Twitter handle too. I think we're O19S as a joke on L18N because Open Source Connections is a huge name. I am omnifrutal because I'm good at all the frutals in the world. But OMNIFROODLE on Twitter. And if I don't know the answer, I'm happy to direct it around. Open Source Connections has a good blog going on right now too. One of my colleagues, Doug Turnbull, has been doing a lot of examinations on how we make decisions about big data storage. And if you haven't been reading it, I really recommend going and looking at it.
Yeah, so there are some great resources out there and also a very friendly community, you know, people just really willing to help. Datastax.com has a lot of information. Planet Cassandra is a good place to go for level set information as well. And then please join us for our next webinar. So, Matt, thank you very much. You can tell John that we say you did a fantastic job. We will have you back. Sure. And, you know, maybe you and he can team up on a future webinar. So thank you very much. Thank you, everybody. We really appreciate your attendance today.
Thanks, everybody.